So let us now check how this equation which we derived for the general transport behavior takes the form for individual cases. Let us first talk about the heat transfer. Now the equation for heat transfer, the flux for heat transfer, which is dependent on Z, is given by Fourier's law, and we know that Fourier's law is basically the flux will be dependent on the temperature gradient. So I'll have some term like del T del Z, special gradient of temperature, and times the constant with a negative sign, and that constant we write as kappa. So this is the Fourier's law for heat conduction, where kappa is known as the coefficient for thermal conductivity. Now, using the relationship which we developed for ZZ, the question is how can we actually get a mathematical form or some formula for kappa. Now let me just rewrite the value of ZZ. So it is 1/3 minus 1/3 average velocity times the mean free path and times the number density multiplied by the quantity that is being transferred and divided by special derivative. Now here what is Q? Now Q is basically the amount of energy, because it's a heat transport carried by every molecule. So it's basically heat transport per molecule. So Q is nothing but suppose per molecule I'm just writing it as epsilon, which means it is nothing but the total energy. So suppose if U is the average energy carried by 1 mole, or U bar, something like we can write, it is U bar divided by the Avogadro number. So that will be the energy carried by each molecule on average. Also we see that this derivative, this partial derivative with respect to Z, the reason we are writing partial derivative because it can also vary temporally, and we will see a special case where actually we have the quantity which is varying not only spatially but also temporally when we discuss diffusion. So in this case the n star, the number density usually does not change, because when you consider heat conduction, so it's a conduction phenomena, not the convection phenomena. So for thermal conduction, so it's a fixed law for thermal conduction. So conduction by definition means that the molecules or the particles does not move. Rather actually in the molecular picture will be they vibrate and at the same position, and they transfer the heat to the neighboring molecule, and that's how the heat conduction works. So the n star or the number density does not change with can just change spatially. So there is no density gradient. So we can actually take it outside the differential, and so it will be nothing but del Q del Z. As we said, Q is nothing but average energy, or you can say internal energy. So del Q del Z will be nothing but 1 over Na del U del Z. Now you see here we can actually replace it, minus 1/3 V average lambda n star and then 1 over Na. We can write del U average del Z, but see here that we have in the original definition of Fourier's law del T del Z. So we have now del U del Z. So we can easily convert it. So we'll take del U del T. We can write the differential like this. We know that if I have a function like this, let's say del F del Z, I can actually write it as del F del X into del X del Z, and we are going to actually use the same formula. So lambda into n star 1 over Avogadro number, and we are writing it as del U del T into del T del Z. Now you see, what is this quantity? Del U del T, it is basically change in internal energy per unit temperature. So this is also internal energy per mole. So this is nothing but the heat capacity, and heat capacity per mole, because we said that it is U bar, it is average energy per mole. So what we get is nothing but minus 1/3 V average lambda n star Cv bar. By Cv bar I mean that heat capacity per mole divided by the Avogadro number into del T del Z. Now we see this entire quantity is kappa. So kappa is nothing but average velocity times there is a one third of average velocity times the mean free path times the number density times the Cv bar divided by the Avogadro number. So thus we see that how we can get a very handy expression for the coefficient of thermal conductivity using the fundamental relation that we derived for any transport phenomena. And now we'll see for thermal conductivity the Fourier's law is there. This is a phenomenological law, and similarly for say mass flow, which is diffusion, we are going to discuss diffusion later. First we can actually discuss let's say viscosity. Now for viscosity there is a relation, and it's known as Newton's law for this viscosity. So let's see the formula, Newton's law for viscosity. Now before I write down the law, let me actually tell you what is transferred in when you talk about viscosity. Now suppose again along z-axis I have several layers which are actually separated by the distance which is equivalent to the mean free path. Now the question is, so this is along z-axis. Now we also have molecules moving in the x and y direction. Now let's say this is x direction. Now what is transferred across the z direction or along the z direction is the x component momentum. So that is a little bit difficult to perceive, in the sense that it is the x component momentum that is being transferred. So what we say here is that we are talking about a gradient along z-axis, so it will be still a partial derivative with respect to z, but the quantity here is that how the Vx is changing. And if you remember that if that changes, like suppose a fluid is flowing, you have seen this kind of picture probably, and then we say that due to friction, suppose this is the wall of the container, and then we say that the layers of the fluid which are close by here will have a very slow velocity than the layer which are at the center. So sometimes actually it is written like the fluid actually flows like this. The reason is just because of the fact that the x component momentum has a gradient along z. So this is z and this is x. What is Newton's law? So Newton's law is again some flux which is the viscosity equation which is a function of z, and that will be negative of the gradient of the momentum, which is nothing but m into Vx. M is the mass for each particle, del z, and times you have eta. So eta is known as the coefficient of coefficient of viscosity. Now although it's a momentum gradient, usually in Newton's equation the mass is not written, so we will have to introduce a quantity mass, and then we can easily connect it to this equation, and then figure out what is eta in a similar way. Now let us just write it. What is the z? It is rather straightforward, the viscosity equation. So it will be nothing but, in our notation it is minus 1/3. You can go back and have a look. So it is minus 1/3 V average lambda, and then you had del n star and Q, and then we can just write it like this, del n star into Q and del Z. Now when the fluid is flowing, in this case also what is happening, the layers are basically parallel to each other, and that's why there is no turbulence in the flow, and this kind of liquids are known as Newtonian fluids. And then what happens here is that as the fluid flows, only the momentum gets transferred. So we can say that as before, just like the thermal conductivity, here also the number of particles are not changing, so that n star we can actually take it out of the differentiation. Also in this case, Q is nothing but the momentum, so m onto Vx, the x component of the momentum. So we can readily see that it will be minus 1/3 V average lambda, and I have n star, and then it is del Q del Z. But remember that Q is also m into Vx, so ultimately the m also comes out because it's just a constant, it's a mass of the mass of each particle. So you'll have del Vx del Z. Now we can easily compare, but before comparing I will just make one more simplification. So it is minus 1/3 V average lambda, and then you see that n star into m, n star is number density times mass, so that we write as rho, or basically the mass density. So that's why I did not use the rho notation for n star into Q in the earlier pages. So now you can compare and you can get a expression for the coefficient of viscosity, or viscosity coefficient. It is nothing but 1/3 V average, and you have lambda into rho. So thus we get another expression for another quantity, so which is the coefficient for viscosity, or a viscosity coefficient. So this is a viscosity coefficient. Now we'll talk about diffusion. Now diffusion is very interesting, and it is a very well studied phenomenon. Again, the treatment we are doing for diffusion is a very simplified phenomenological description. Now for diffusion also, just like for thermal conductivity we had Fourier's law, for viscosity we had our momentum transfer, we had Newton's law. For diffusion we have Fick's law, and this law we'll first write it as instead of calling it as a Fick's law, we'll call it as a Fick's first law of diffusion. There is a reason why I'm calling it as a first law of diffusion. Sometimes some texts will write it as a Fick's law of diffusion, some texts will write it as a Fick's first law of diffusion. So that says the quantity, in this case the flux, which is basically the particles itself, that is equivalent to the concentration gradient. Now this is pretty straightforward in this case, because if you just compare with our generalized equation, which is minus 1/3 V average lambda del n star Q del Z, and remember that in this case Q is just nothing, Q is 1, because it's the particles itself, how the n star is changing. So you can readily figure out what is D, and diffusion coefficient comes out to be 1/3 V average into lambda, which is very straightforward. Now the interesting situation will happen when we say that this quantity, which is Zz, so that also is varying with time. Why this happens? Because among all the examples we told so far, this is the only example where we talked about the n star itself has a gradient. So basically, and the particles are basically moving, or the molecules are moving. Now you can think that suppose I had a high concentration region and I have a low concentration region, and particles are moving from high concentration to low concentration. Now what will happen over time is that as the particles are being moved, the high concentration or the concentration in the high concentration region will fall down and the concentration in the low concentration region will increase. So basically this del n star del z, that will be time dependent itself. So n star has a time dependent, or the basically the concentration itself has a time dependence. Now how will you incorporate this time dependence? Now there is a very easy way to incorporate it. Suppose again we'll consider two layers here. Suppose this is one layer which is let's say at a position along z, arbitrarily I am calling it as z, and there is another layer which is at position let's say z plus delta z. Now the question we are asking is that how many molecules are basically accumulating, how this n star is changing with time, that we can easily calculate by considering what is the net flux basically changing for the bottom one and net flux changing for the top one, and then if we take the difference from that, actually we can calculate how many molecules are getting accumulated in this region, in this volume which I have shown as a rectangular volume. So now the thing is that that you can easily calculate. So how do you calculate it? Let us do it very systematically. So let's say what I am saying here is that I want to calculate the delta n, which is the delta n star, because we are using n star notation, per unit time. Now what it will be? So suppose in this particular volume, now again n star, remember it's a density, so you have to divide again. I will first calculate, suppose this surface has some area, suppose the area is A for this as well as for this, the area is A. And then what we are going to calculate, we know the flux. So flux is number of molecules changing per unit area per unit time. So suppose in delta t time, the flux basically changes by this amount. So right now I am writing z as a function of both z as well as t, and if this is the flux, the number of molecules which are entering this area, so per unit time, it will be nothing but times the cross sectional area, because per unit time is already there. So what we are going to calculate is change in the density per unit time. So this is basically the amount which is being gained, and we also have to divide it by the volume. Now the volume is nothing but A times this length, and this length is z plus delta z minus z, which is delta z. So this is the number of molecules which are entering per unit time, because per unit area we have multiplied here, and then I have to also make sure that number of molecules are also leaving through this surface, which is the surface which is located at z plus delta z, but there the flux is slightly different and at time t, and into, if I just multiply the area, so that will be the number of molecules leaving that surface per unit time, because I have multiplied by already the area. So then if I divide by the volume, so that is basically the number of molecules leaving this total volume. So that you can easily reorganize, and you can see that this A cancels in the numerator and denominator. So what will be left with is basically the flux at z, it will be flux at z divided minus flux at z plus delta z divided by delta z. Now of course you can now approximate that this delta z which we have chosen is much small. So in the sense that the limit delta z tends to 0, now this quantity becomes by definition, it's basically the derivative of the flux with respect to the position. And also to write it consistently, we are writing the z as a function of z, the position, as well as time here. So in that limit, we can write that this change which we calculated is nothing but the differential change per unit time, which is basically the time derivative of the concentration, and that is nothing but the special derivative of the flux. Now, if you note carefully that by definition, suppose what is definition of dy dx, we just write it that it is the value of y at x plus delta x minus value of y at x divided by delta x in the limit delta x tends to 0. Now, in the same token, you see that there is a negative sign because I am talking about z at a position z plus delta z, but with a negative sign. So it should be, there should be a negative sign here. But we know that this thing is nothing but the negative gradient, special gradient of this quantity z, but for z already we have the fixed first law, which is nothing but this. So you already know. So let us just put it back. So what we will have is that there is a minus d into del n star del z. N star depends on z as well as t. We are just writing it very explicitly. So what we get ultimately, the time derivative of the particle density is equal to the second derivative of the particle density, and this is basically a second derivative in space. So this equation, this law is known as Fick's second law of diffusion. So Fick's first law actually talks about connects actually the coefficient of viscosity. I mean, basically it says the flux as a function of special gradient, but as time progresses, the flux itself changes because the concentration gradient and the concentration itself is changing with time, because as the molecules move, the concentration must change with time, and so the concentration gradient changes, which means the flux itself changes. And so to incorporate that, we figured out it is nothing but the very nice equation that the concentration gradient with respect to time is nothing but the second derivative of the concentration with respect to space. Now, this is a very important equation in hydrodynamics, and it has a lot of like applications. And one interesting analogy, although this has nothing to do with this course, is that the time dependent Schrodinger equation, which is actually the Schrodinger equation. Schrodinger equation means it's a time dependent Schrodinger equation. So when you write it, you will see that the time derivative of the wave function is basically the gradient of the wave function. So it's basically the kinetic energy and potential energy, and kinetic energy has, if we write it more explicitly, so it's basically the Hamiltonian, and then we can write the Hamiltonian as minus h bar squared by twice m and del squared. Now del squared is nothing but the second derivative with respect to space and some potential energy acting on psi. Now if you look at this part, like on left hand side I have a time derivative, and on right hand side I have actually double derivative with respect to space. So that's why it's of course known as a Schrodinger equation, but Schrodinger equation is not exactly an wave equation, because what you do in wave equation, when you talk about suppose you just take a classical sinusoidal wave, and if you talk about the amplitude as say psi, you will figure out that if you do the space derivative and the time derivative and use the definition of the velocity of the wave, then you will find that that wave equation will have something like del 2 psi del t2 will be equal to del 2 psi del x2 with some production constant. It will be 1 over v square in this case. Yes, so v into x. Yes, so that's how it will come. but or it will be the 1 over v square in the other side. So it's a time derivative. Yeah, so then what you see here is a very interesting thing, that here actually on the either side we have double derivative in time and space. So this is the wave equation, but Schrodinger equation is actually, strictly speaking, although it is a wave mechanics, because we talk about the wave particle duality, and particles also have wave nature, and from that it the entire thing stemmed. But I mean, like, mathematically, the Schrodinger equation is more close to the fixed second law, where actually the first derivative in time connects it to the second derivative in space. So this is just to give you a feeling, like how things are, although we are talking about very different physics here, but how things are connected. So so far whatever we have done is basically, let me go back. We derived the equation for the generalized transport, and then using this equation we said that we can always define a flux, that is the most important quantity, and this flux depending on the particular phenomena you are describing, the phenomena can be viscosity, the phenomena can be diffusion, the phenomena can be thermal conductivity, and you can actually get a coefficient phenomenologically. And using the analytical expression that we derived, you can actually get a mathematical formula for those coefficients, like we derived it for the viscosity coefficient, like we derived it for the thermal coefficient kappa, and also we derived it for the diffusion coefficient. And particularly for diffusion, we found that this quantity, that del n star into q del t, the n star itself, sorry, del z, the n star itself is changing here. So what it means that as it changes spatially, things are moving from one side to another side, which means over time also you will have dynamics, and that's what we figured out here. And we found that the very important relation, that the first derivative of the concentration with respect to time is nothing but the second derivative of the concentration in space. So we'll stop the discussion here, and in the next section we'll be talking about the transport properties of ions, which is slightly which will use slightly different treatment there, because for ions there are a lot of electrostatics involved, and then whatever we have studied, this diffusion coefficient of thermal conductivity, although thermal conductivity is not very necessary for our discussion, and viscosity, so particularly diffusion, those will be important when we will discuss the reaction dynamics in solution. So those things will be useful, and there actually will also talk about a little bit about the reaction between ions using the conductivity of the ionic, not ionic conductivity, it's basically transport of ions, a movement of ions in solution. And also we'll see at the reaction dynamics section, we'll discuss about the electron transfer reaction, but from a very different point of view, from the potential energy surface point of view, which is nothing but the Marcus theory of electron transfer.